perfectly happy. This is not original to me. I borrowed it from Ed Hare at W1RF5 to the ARRL Labs. This is his terminology. We're just going to go over a little microcontroller basics review. What is interfacing? We'll talk about some interfacing and a little bit of, this is going to be more pseudocode than anything else. Not processor specific, just some techniques to refresh yourself that you can use in your own projects. And by no means am I the expert on this. There's probably people in the room that know this stuff better than me. So, and just remember that and be kind and gentle with your comments. Okay, what is a microprocessor? And some may say, what's the difference between a microprocessor and a microcontroller? A microprocessor is an integrated circuit. It fetches an instruction, it executes an instruction. It is a glorified slave. It takes an instruction, it executes an instruction. It fetches the next instruction, and then executes that instruction. And it's not, it is not the sentient being, it is just a slave that does what is programmed. Now, what is a microcontroller on the other hand? Microcontroller is the integrated circuit that not only contains the microprocessor, the CPU, but it also has your program memory. It has program ROM, which is in Windows desktop terminology comparable to an SSD, a solid state drive. It has input-output ports. It's literally a computer on one chip. Our smart devices, smartphones, they're an example of a microcontroller. Microcontrollers now, and the lines between microprocessors and microcontrollers are even becoming somewhat blurred. They're not totally separate lines anymore as technology increases. ST Microelectronics turned out a microprocessor and a microcontroller on one die, a slave microcontroller. I think it's called the MP1 if memory serves me rightly on that, which was quite an intriguing product when I saw the review on it. And now we're going to see the difference between a microprocessor and a microcontroller. Microprocessor, typically your data memory for having variables open, program memory, which is the preferred terms to call it, peripherals, they're outside of the die. In the old days, how many of you remember? Some of you remember the Z80. The Z80 had a PIO and an SIO chip, serial input-output chip. And a peripherals input-output chip. They had SIO, PIO chips. Your Motorola 6500 line, I think, had similar chips. They were on external chips. They were outside the microprocessor itself. They were on another chip, another external component. But it must be 12, at least 3 minutes. There it goes. Maybe it's going to work. No, that's all right. Let's go back. There we go. Your data memory, your program memory, and peripherals, they're all on one die. They're all in one integrated circuit. And there's a nice little figure I found online. You can see who it's attributed to. I did not create this graphic. I found this on the internet, which illustrates so well. You can see the microprocessor. It'll have input-output ICs. It'll have memory, and data and program memory on separate ICs. As a matter of fact, the Raspberry Pi Pico, you're going to find this to be amazing. The actual chip itself, the RP2040, its program memory is external. But on the Raspberry Pi Pico board, it's on the board. So you can have external memory, but they put it on the Raspberry Pi Pico board for you, and to make it easier to develop. And I apologize for not having the Raspberry Pi Pico program ready, but with everything going on, I've not had time to finish it. And you can see the microcontroller, it's got it all literally in one die. It's all in the same, in the silicon real estate. And that way you don't have to go out and buy these extra pieces. You can buy one microcontroller, and I find it interesting. We're having a program this afternoon on how to pick the right microprocessor or microcontroller. KX4TT will be doing that, and it may be in the primary track, or it'll be in here, I haven't decided yet. Over our noontime meal, we'll straighten that out. Because John's doing his program remotely in the primary track next door to us, and he had the secondary program in the afternoon, but will not be here. So we may be moving that up into the primary track. Okay, come on. There it is. What is microcontroller interfacing? You just can't simply attach a device to a microcontroller. I mean, it either will not function or it will damage the microcontroller depending on what you put on there. It's just, it has to have some kind of interface. You just can't hook a device to it. Come on. Maybe And I put this in the notes, your microcontroller is more than likely probably damaged or destroyed if you just simply hook it up. Can't do it. It must be properly interfaced. 3 categories I came up with, and there may be more. You may categorize them differently, but this was just a jumping off place to start with. We have output interfaces, input interfaces, and advanced interfaces that can sometimes have both or other things. It can be a mixture. Let's go into some of these. There it is. I like this little picture here. It illustrates it really well. That was on the Pickaxe website. It was part of it, and you can see various input devices are interfaced to the microcontroller, and then you have output interfaces for output devices. You don't just simply hook them up. They must be properly interfaced. There we go. Now let's look at an overview of some interfacing techniques, and I'm going to push the button. These interface techniques are virtually used on all microcontroller platforms today. And these are not all the techniques that are out there. I'm just showing you some of the more popular ones. There are many more, but these are just good ones you can start with. And as you begin to tinker yourself or continue tinkering. And I'm going to use pseudocode. And the graphics in this I did borrow, and I give the credit, is from the Pickaxe Basic Manual number 3. Now Pickaxe is a series of microcontrollers that they took a PIC microcontroller, programmed a proprietary version of BASIC on it called PBasic. And it's done by Revolution Education Limited. And you can program it, it has a basic interpreter that runs on this PIC microcontroller. And I borrowed a lot of the graphics to them because they were already done. It made putting the program together a whole lot easier. But to them, I give all the credit, and there is the link to the manuals there as well. Okay, the following are examples of common output interfaces. We're going to talk about output interfaces. We're going to go through these quickly because of the time, and I can't see the time, so somebody like to keep it, let me know when it's about 10 minutes till noon. Somebody could do that. I appreciate it. My phone is in there for the audio for that.
We still got half an hour.
Oh, good deal. Very simple. Now, one of the most simple interfaces, you could use this. This is the Hello World software test for the very first program you'll ever write. And you know, when you're programming BASIC or programming in C or whatever, you make it say Hello World on the screen. That's an example. But this is an output technique used for a Hello World program with microcontrollers. You can see pin 1 going to, again, these pins are referencing to a Pickaxe microcontroller, just so you will know. You can see that you have the, I can use my mouse pointer to illustrate. You got your light emitting diode, your LED, you got a current limiting resistor. That is essential because this is 5 volts. Now a lot of modern microcontrollers today are 3.3 volt outputs. And now I'm going to ask Gordon a question on that. Do they still use a current limiting resistor even with a 3 volt output if they want to run an LED?
Yeah, you better.
That's what I was thinking. Otherwise, your LED will not like it because it typically don't like more than 2. It'll tolerate 3 volts, but it will be very bright and may not last too long. And on 5 volts, it will glow even brighter and not last long at all. And if you put 12 volts to it, it'll go like a firecracker. When I was breadboarding up I wrote an article in the April 2016 issue of QST magazine on a little simple Pickaxe-based timer. It was like a one evening project. When I was breadboarding it up, I hooked up the LED by accident around the dropping resistor. That resistor right there, I can't see my mouse. Now, I forgot that resistor when I was initially breadboarding it up. And when I hooked it up, it didn't glow red, it almost glowed white, and then went pow! And shot the lens of the LED. You can see where it fractured the lens, and it shot that lens like a firecracker, boy. So, say, how many of you blew up capacitors in electronics school? I know I did. We put them behind the shield, put too much voltage to one, or no, we hooked up the first one backwards, and it actually went like a firecracker, went pow! It almost left with some leads and some paper and foil. Then we put another one, the correct polarity, and put too much voltage to it. It actually went and then went like a firecracker. That is very essential, and you could damage your microcontroller port with excessive current. This computer's being a little bit slow, I can see it. But yeah, this also limits the current coming out of the port as well. There are 2 terms, I should have put these in the slides, that you need to know. Your device can be current sinking or it can be current sourcing. If it's, this one's current sinking, because it's taking the current out of pin 1 and sinking it to ground. If you have it connected, your output, and it goes to V++ or plus 5 volts with a limiting resistor, that is current sourcing. And your microcontroller, that can be set up either way typically, and depending on how you design it. But this is in a current sinking application, because you can see here, and again the mouse is very slow. Output technique number 2. In this case, you notice it's in a current, the other one was current sourcing. This would be current sinking application. The first one was current sourcing. This is current sinking. Notice it's 5 volts, and it will sink the current then to ground through that pin. Notice again the current limiting resistor is still there, and it will still work, but it's sourced to 5 volts. You would apply ground, turn that pin low. You can see in the to switch the LED on, you have to switch it low. In this case, that's pseudocode. You can see there from the pickaxe. You make that one low, it turns the LED on. The other one, you'd have to make it high to turn the LED on. And that is the difference between these two. Same components, but one is in current, this is current sourcing, the other one is current sinking. In this case, oh, I got it backwards, I'm sorry. This is current sinking, the other one is sourcing. I get I tongue-tied. Well, anyway, there's a bicolor LED. You could actually do a high on 0 to switch on the red LED. You could then do a high on one pin to switch on the green one. And switch off the LED, you do low on 0 or low on 1. And depending on which way you do it, will determine which polarity, because you can see the LEDs are biased the opposite way. So this is where you use a bicolor LED with a current resistor going to 2 pins. You turn whichever one you want high, whichever one you want low, to determine the current direction. And you can make it high or low that way. For example, if pin 0 is high, and let's see, pin 1 is low, it's red. The red LED will conduct. If you reverse them, make low go to pin 0, and high we go 5 volts. The pin 1 on this particular microcontroller could be 3 volts. It'll make it green in color. And you can make it with code switch back and forth. Old-fashioned lamp, number 4. You couldn't put that on a microcontroller pin. It would damage that port on that microcontroller. So you use a transistor to take pin 1, when you have ground on one side, 5 volts on the other. The lamp will be the current limiting resistor, and this is just a good old 2N2222 or whatever. You could use that. And that's the lamp itself would be the load that the transistor supplies. Now you want to be sure, depending on what the lamp is, that the transistor is designed to sink that current, obviously. Because it's going to be a current sinking mode in this case. The transistor is. And so when you put 0.6 of a volt on the base of that transistor, and of course you got a current voltage dropping resistor there, drop 5 volts down to about 0.6. Because from the emitter of the transistor to the base, and that resistor would have to be 5 volts. It has to be able to drop 5 volts. The resistor drops about a little over 4.2, 1.3 volts, and then it drops 0.6 or 0.7 when it's fully turned on. And you apply 5 volts to pin 1, it turns on the emitter to base, and then allows current to flow through the collector. As you know from your fundamentals, those of you that are familiar, a bipolar transistor is a current control device. A MOSFET, an FET, is voltage controlled. It has a gate, and it operates very similar to a vacuum tube. It works on a very similar principle. On a standard FET, your gate's similar to the grid on a vacuum tube. It has a negative voltage, it pinches off current flow. Or voltage, excuse me, it's a voltage. When the voltage applied to that device, the current from drain to source comes to a stop. And in a tube, it's from cathode to anode. But you can see they're very simple technique. Piezo buzzer. Notice the circuit is very similar. Your buzzer is in the place of the lamp. But you notice that diode across there. That's to prevent when the buzzer quits sounding, a counter EMF from being generated and put a spike through the system. It would not, your microcontroller would not like it. Notice the circuit's almost the same. It's got the same dropping resistor there across the base to the pin 1. You run pin 1 to high, the current close to the transistor, and the buzzer goes like that, for example. Now I know what the problem is. Number 6, piezo buzzer. Very simple technique. You can see the circuit there is very simple. Now you can use a 40 ohm resistor with the the pickaxe controller, notice they use it's a 40 ohm speaker with a 10 microfarad cap, and you can hook it up that way. But that's with the pickaxe controller. But a piezo buzzer is such a low load that you can interface it directly in many applications. Now I know what to do with this. Now here's the big daddy when you want to turn a motor on and off. Again, notice the diode is across the motor. For the counter EMF, when you turn the motor off, it don't produce a reverse EMF across it. Because remember, the motor is an inductor. What's going to happen when you turn the power off? It induces an opposite, a counter EMF right across the windings of that motor. So you need a diode to clamp that reverse voltage. And the circuit, you notice, has still got the bipolar transistor. It's got a 1K dropping resistor. Turn pin 1 on, turns the motor on, because it turns that transistor on. Same similar technique. And there's, I think, with a MOSFET transistor. In this case, you got a 10K resistor going to ground there. That's a MOSFET transistor. Now this is a voltage controlled device, not current controlled. And that therefore is the key difference. Just a general MOSFET, because you can see the insulated gate there. On a standard FET, the gate, actually will be physically connected. But on a MOSFET, you have a physical glass insulator. That's why a nuclear EMP, if it happened, if the Chinese decided to do an EMP, it'd wipe out all our modern electronics, because every gate to drain a source would be shorted on all these modern devices, and they would go, bye. Relay. Notice again, the same transistor, the same current limiting resistor there. This is a bipolar transistor, and you're turning a coil with a relay on. When you turn that transistor on, it provides a current flow through that relay coil, and then the contacts on the relay operate. You can operate a very, very high voltage. This could be controlled with 220 or 440 volt circuit on the contacts of the relay, but it's only low voltage on the relay coil. 7-segment LED. Notice here that this is a BCD input. So you're going to have 4 binary digits, with which 1001 would be 9. That's a BCD input, for example. And you can see the 4 pins right over there. And those 0000 would turn on segments, let's see, F, E, B, C, D, and A, for example. Numeral 1 would be B and C segments only. If you put, let's see, 0001, that'd be a high to pin number 1. No, pin number 0, I'm sorry. That'd be binary 1. That turns into, let's see, because 0 would be a low voltage on all 4 pins. That'd be binary 0. Remember your fundamentals. 0 is a number in binary. That's what they always reminded us with in electronics school. And in programming school, 0 is still a number. All right, this is let's see, I think I went back. Okay, yes I did. This will be a little simple LED clock. This is a chip that, if I recall rightly, it has if I remember correctly, let's see, I'm looking at pin 1, that's reset, F and G, those go to the segments. See, those pins 13 through -8, let's see, 13, 12, 11, 10, and 9. 7 to 6 go to your 7-segment display. And then pin 0 is a clock pin, so it would count, is my understanding of that. And there's where you could do a 2-segment, driving 2 chips, one cascades into the other. Time don't permit us to get into that. And let's see, the clock pin, let's see, the output, the first chip will clock the second one. So that way it counts 0 through 9, then it clocks the next one. Input interfaces. Again, I told you this is nothing profound. Most common right there. Take pin 0, if you push, it's to ground all the time because the 10K resistor will pull it to ground. The switch will put 1 on it. Now you've already, those of you that know, saying, well, there's a problem with this. You're right, there is. There is a problem. But let's get to that in a moment. Here is the other way, where it will be pulled up high all the time with the 10K limiting resistor, but then the switch will put a low to it. Depending on what you want, how your circuit's designed, you may want to put a high to it or put a low to it with a switch. And again, same problem. If you push that switch and it needs input, it's probably going to input about 100 times. And now I'm going to illustrate why. And let me get past that in a moment. I'll talk about that in a few moments. The problem is that switch must be debounced. If you don't put debouncing in there, it will read that switch 100 times and I'll show this later in the program. Here's an analog input technique. You want to measure 0 to 5 volts. And a lot of microcontrollers have an analog to digital port on them. It will measure an analog voltage. You could have a potentiometer connected to it, and then vary the voltage to it. You can read a varying voltage on the input. For example, that's what they use there. If you want to have a potentiometer you want to control something with, you can do it that way. Or if you just want to read 0 to 5 volts, you can do it that way also. You go to CDS photoresistor. A photoresistor that varies its resistance depending on the sunlight. And of course you can see there it's pulled to ground. If I recall correctly, I believe it, let's see, the resistance I believe drops in sunlight, or does it increase? I think it drops in sunlight. And I think it's got more resistance when it's dark, or it's the other way around. But depending on what the light is, it varies the resistance of the photoresistor. And you can vary that, and you can measure that voltage on there to an analog port and determine how much light you're getting, roughly, once you calibrate the system. That's a typical example input. Thermistor. Notice that you replace the photoresistor with a thermistor. Notice the circuit is the same. And you can measure temperature with that. And I believe it's, depending on the thermistor, what's the most common design? I think it's, decreases, as it increases in temperature, the resistance decreases. I think it's the most common design. It's what's called a positive coefficient, I think it is referred to. But yeah, the most common is that the resistance will drop as the temperature increases. That's the most common. They may make some that are the other way down, but that's the most common. And you measure that between, remember that that 10K resistor pulls it to ground. So if that thing conducts all the way, you still got a 10K limiting resistor to limit the current, whether it be that thermistor, whether it be the photocell, or whatever the case may be. I'm not sure if keyboards is playing this stuff. And so that also then limits the current flow down to a very minimal amount of current. There's not a lot of current's going to flow. This is an infrared receiver that actually has a clock out of it, depending on what it gets. I've never played with one of these, but an infrared receiver can interface into a microcontroller. And depending on what kind of microcontroller it is, if it's only 3 volt inputs, you'd have to do some translation. And depending on the infrared receiver, it has a 5 volt output or 3.3 volt output. There's a lot of stuff now that's 1.8 volts and some of the higher end stuff. And you can see there they're pulling it high with the input pin there with a 4.7K resistor. You can see it right there in line. They're pulling it high and the device goes low. Pin 2 of the IR receiver provides ground. Pin 3 provides power. And that cap in there is what Gordon mentioned in his previous hour, power supply filtering. It was amazing that the 3300 microfarad cap cleaned a lot of that radio up. That was simply amazing, which I found to be fascinating. Okay, here's a few advanced interfaces. Serial LCD. Now this is one you play with a lot in microcontrollers. It'll have a serial data stream going into the LCD, and the firmware or the driver chip will then control the outputs of the actual LCD itself. And typically these little cheap, $5 displays, buy them on Amazon for that. They have a contrast control to set the contrast on. These are very common. And there is a 44780 right there, probably. I think that's a 44780. You can see whether it's got a read-write pin. This is parallel input here. This particular one, it's got parallel input. And you could have a chip that would take that serial data and translate it to parallel. But this would often, I think on the 44780, I think it has that, maybe if I remember rightly. But this is just some examples of some more advanced techniques. Okay, this is the parallel one without the serial to parallel conversion. And notice you got current limiting resistors on each of the pins there, and coming in on that. We know what RS-232 interfacing. Here's a poor man's way of doing it. And this is with the pickaxe, because the pickaxe, you have to have that 22K resistor and 10K resistor on those pins to stop it from going into programming mode on the fly. Otherwise, it'll go into program mode. So you always have to use those two in a pickaxe design. But in a regular pick and other controllers, you wouldn't need them for that purpose. But you can see here, that's what they use for. But let's go to the more common serial interface techniques. How many recognize this chip? The Max 232, the good old Maxim, which now is owned, I believe, by ST. Who bought out Maxim? Was it ST Microelectronics, I think, in about a year or two ago? I think ST bought them out. But the Maxim 232 has been around forever. It's a RS-232 transceiver IC. The voltage levels in RS-232 properly are plus and minus 12 volts. Well, a 5-volt microcontroller don't handle that too well. They don't like it. And so you would therefore take the data out of your computer, would be on TXRX, or excuse me, pin 0, pin 1 for the pickaxe. TXRX would then be the outputs going to an RS-232 circuit. And you got the various 10 microfarad caps. One of them is probably clean the power supply, and the other is functions required by the RS-232 transceiver IC. But it makes interface in RS-232 essential, this is a very common technique. If you know, because the RS-232 port is still around. It's around in microcontrollers anyway. Okay, now I'll just discuss these. The SPI port, developed by Motorola, it's now Freescale. It has a 4-wire serial bus. You have a clock, you have a master output, slave input, master input, slave output, and a select line. Now, I have read it's faster than I2C, and I can see why. But each of these, and the next standard, I2C, each have advantages over the other. Which one do you pick? Depending on what peripheral you want to interface, usually. Some peripherals are called SPI, and SPI is pronounced SPI. You'll hear it pronounced that most commonly. And some are I2C interfaces. We'll discuss those in a moment. But here is a sample of a serial or a SPI interface. You got your master controller on the left. You can see they all share the same pins, but you use the chip select pin to select which slave you want to go to. It depends on which one. And the master will select which that SS1, SS2, and SS3 not, I should say. Not, because it has the not symbol over. It's a select load. It takes an active load to select whichever one you want to go to. But they all get the same clock. Master out serial in is data going from the master to the slave. Master in serial out is data going from the slave back to the master. And that's how the SPI works. I2C, developed by Philips, which is now part of NXP. It's a master-slave configuration, but it's different. It's not synchronous, it's asynchronous data. The sync line on your SPI that's your chip select. It's different. It's got a clock, excuse me. The clock pin is separate from the data pin. Your clock and data are on separate lines. On the I2C standard, they share. And you have two serial, you have a clock and a data line. There is no chip select with the I2C device. It's a little slower, but it's a lot less pins. And there's your diagram there. I got those from Wikipedia. I didn't create them myself. You don't have a chip select line here. You don't need that anymore. You simply run a clock and a data line. And notice you don't have two data lines. You've got one. In other words, data in, data out goes on the same data line. It takes less wires to do it, but it will be a little bit slower naturally as a result. Okay, let's see. These are pickaxe basic codes here. There's a little bit of code right there. If you want to turn the LED on, and this would be the code for and it's in basic for the pickaxe controller. You tell pin 4 on the microcontroller go high, and yeah, I didn't do my graphics very well. I did this in LibreOffice too, so Gordon, I understand the heartburn when going from LibreOffice to PowerPoint. And it has a pause of 1,000, actually it's not there in the diagram, which is 1 second. It goes low, the pause 1,000 is a command to basic, tell it to wait 1,000 milliseconds. Then go to main, which procedural programmers hate to they like go sub because that's more structural. Basic has go to, C does not. And because that violates.
6 minutes.
Oh, are we at time?
You have 6 minutes.
Okay, all right, let's sign down 44 after. Okay, let's get into this. 7-segment LED interface. There's some code right there to, it would count from 1 to 9. Let pins equal B1. That does a pause of 1 second, and then it's a loop that would cause it to count. It's simply a loop, and that would cause this circuit here to count. And it will load then from B01, which is, and that should be that port, I believe. Let pins equal B1, and it sets up this. It's just a for loop. That's all it is. It's a for loop. It loops through, and then it goes back to the loop and starts all over again. So this will count 0 through 9, then go back 0 through 9. It's just some sample code. This would, again, this is for the pickaxe controller. Now, we talked about demounts. What happens when you press the switch? That's what happens. That's about typical for a press switch. If you have a circuit count, each one of those will count as a switch contact. It's horrible. There's 2 ways you can do it. You could do it in hardware, or you can do it in software. When I did my timer, I created a delay. I had to hold the switch so long, and when it was in that state, you would read it. A lot of techniques today is often used to debounce it in software. You can do it in hardware with a capacitor. But you can see there, you hit that switch, it's going to jitter until it makes full contact. And there's the code right there with has the delay in it. And without, the code on the left is without debouncing, the code on the right is with debouncing. Notice they dropped in a 100 millisecond delay on that command before it began to read that port. So you can see right there, you put in a 100 millisecond delay, so that way if you have the switch down 100, it counts it. If it's less than 100, it don't count all those bounces. And that's a great way to do the signal debounce, is using a delay. Reading a thermistor or a cadmium sulfide cell. There's a code right there. It reads different voltages on that pin. The ADC command, that we didn't have time to get into the code on this. You can see the comments there on the right explain it. And a range to 50 and 0 to 50, it will just indicate 4 different levels of light. And it'll light an LED, I think, in the circuit, depending on which one it reads. If I understand it correctly. I didn't have the full circuit in with this to show it. Sending data to a character serial LCD display. Notice those nice little commands they give you. And a lot of if you use a C++ to develop, you'll have libraries that do this for you. And often serial out, and you're setting it for 2400 bits a second. I think no parity is what this command means. And in the parentheses and quotes is what you want to send to the display. Now, those next line is a new line instruction. Pause 1000, and then wait. It'll sit there and flash hello, new line. Flash hello, new line. And it'll just loop forever. But it illustrates the idea of writing just some simple code. And that is a presentation.